So I have the pleasure to invite Jannis Epting from University of Basel. Jannis invests along his hydrogeologist and the geologist working with Basel, and he invested. I've seen several research works published already since a very long time concerning geothermal aspects. So Jannis.
Yes, thank you, Rado. Just want to say it's 10 years ago, and I was at the European Geoscience Union. There was a session also with Mr. Carrera together. I had long hair. I think, if I remember right, you had a moustache. But at that time the topic was aquifer heterogeneity, and today I want to talk about developing tools for the thermal management of urban subsurface resources, and specifically concerning the delineation of boundary conditions. And I will show examples from the case study of Basel City. This shows the horizontal development of Basel through the last centuries, and you see Basel got much bigger and got connected to the agglomerations, but more and more Basel also develops in the height. That is the highest building of Switzerland, it's the Roche Tower. That's the same building also going down up to the bedrock. This picture shows you Basel from beneath with all the subsurface structures and also tunnel roads. In the last years we were able to compile all the information about subsurface buildings, which you can see here in this rosa color. These are subsurface buildings reaching down to the subsurface if they have base floor bigger than 2,000 square meters, or if they reach deeper than 3 stories beneath ground. And you see the dark red buildings. Those buildings even reach until the groundwater table, some of them even down to the bedrock. What you also can see is the regional groundwater flow regime. Groundwater is exfiltrating into the River Rhine. And you see that in the city of Basel, groundwater is extensively being used either by the municipal drinking supply, but also by many industrial users using the water for groundwater for cooling or heating processes, and some of the groundwater is re-injected back into the aquifer. This shows you the development of groundwater usage in the city of Basel. The most quantitatively the most important is the drinking water supply. You have industrial groundwater use, whereas most groundwater is used for cooling purposes, and some of the water is re-injected. If you have a look at the re-injection, you can see that far more water with elevated temperatures is re-injected back to the aquifer than water that has been used for heating, and colder water is re-injected back into the aquifer. So, next to natural processes, hydraulic and thermal processes, in urban areas we also have to consider anthropogenic processes. And these processes often are highly dynamic, and to understand these processes, good quality data are necessary to appropriately capture the different boundaries which describe the hydrological regime of these aquifers. This shows you a quite actual map of the groundwater monitoring system in Basel City. The municipal drinking water supply, they have their own monitoring system, and actually, although some of the observation locations are located at points where they should capture specific boundaries, like here, the inflow to the municipal water supply, most of the locations were selected just to have a quite regular spaced observation network, not looking at specific processes. Therefore, this graph shows you the data from 1993 to 2014, and also the development of observation wells in the city of Basel. You see, in 1993 there were only 18 observation wells, which also measured temperature. In the meantime, we have, I think, about 90 observation wells where temperature and hydraulics is measured continuously. You can see here the trend observed in groundwater temperatures, and below here the trend, it's a slight trend in air temperatures. And normally for natural background aquifer temperatures, I assume it correspond to air temperatures that should be around 11 degrees Celsius. We have for the urban area of Basel, in the meantime, we have temperatures about 14 degrees Celsius. So we have a quite overheated aquifer in Basel. When you have Swiss regulations and you want to use groundwater, you are allowed to change the groundwater temperatures by plus or minus 3 degrees Celsius. So if we assume even not this 11 degrees Celsius, but maybe for urban aquifer 12 degrees Celsius, and think we could change these temperatures by plus or minus 3 degrees Celsius, there's no way of using the aquifer anymore for cooling purposes. As these data I showed, these are all from conventional observation wells, and these originally were constructed to measure hydraulics and to take groundwater samples. They were not measured to get unbiased temperature measurements. And therefore, we installed depth-oriented temperature measurement systems. First, for a pilot area, that was in 2010 at 4 locations to delineate the thermal input boundary, but also for river groundwater interaction downstream of the deep reaching building and downstream of a thermal groundwater user. And in 2014, we constructed 3 further groundwater, this multi-layer groundwater wells, also to investigate inflow areas of densely built areas or residential areas that are currently under construction, and to investigate river groundwater interaction processes. This illustration shows you some data of the 4 first observation wells. You can see, for example, this one that's located downstream of the deep reaching building structure, where you nicely can see the impact of the building structure and the winterly heating, but you can also see the influence of aquifer heterogeneity. So what could we do with all this data now available, and also the data available from all the building structures reaching more or less deep into the aquifer? Orange buildings were those that reach down to the bedrock. We were able to parameterize groundwater heat transport models, and this shows you the results for this pilot area. This is the thermal regime in winter 2010. You can see the influence of the city and the diffuse heat input. You can see the elevated temperatures located around the building structures or downstream of thermal use. What we did then, we take away all the boundary conditions to see what would be a potential natural state, and the difference of those 2 maps give us actually the change that already occurred in the thermal aquifer, in this case for the year 2010. And you can see that at local areas the groundwater temperatures are already elevated by about 8 degrees Celsius. And again, if we come back to the rules for Switzerland, here, these areas, the groundwater temperatures already have changed more than 5 degrees Celsius. So actually only these small areas would be still, would be possible to use groundwater still for cooling purposes. The next slides I want to show to you shows you the boundary conditions and also the dynamics of the boundary conditions. First, for the hydraulics. You can see in the first picture, you can see the hydraulic, that's the groundwater recharge in blue, and the precipitation. Quantitatively, precipitation and groundwater renewal by aerial percolation of the water down to the groundwater is negligible for this groundwater body. Here we see the river level, and in light gray we see that groundwater exfiltration is the dominating process for this area of Basel. Only during major flood events there is also river water infiltration. Then quantitatively very important is of course the regional groundwater flow and the extraction as well as injection of groundwater by the users. This figure shows you the thermal budgets and the dynamics of for the year 2010. You can see here the temperature of the air temperature, then the thermal budget for the upper boundary condition, Then for the river, you see the positive budgets for the summer month and negative for the winter month. Then nearly balanced the one for the thermal regime, and then the input of heated buildings, whereas especially the deep buildings that reach into the groundwater have the most significant impact on the thermal budgets, as well as those like reinfiltration of water that was used for cooling and that heats the aquifer. This shows you the statistics of the data I showed you before. For the hydraulics, you can just see, as you can assume, the biggest variability comes by the infiltration and exfiltration of river water. When looking at the thermal budgets, you see the most important is the one across the river and the regional groundwater flow. If you take those together, they are plus minus balanced. But if you take those that come from the anthropogenic influences, they are positive, so they continuously heat the aquifer. What are we currently working on? We are trying to capture and better understand the different boundary conditions. On the one hand side, the natural boundary conditions, and there it was also in scope of a review process. We had to explain when and to what degree we have to describe the upper boundary condition, the influence of the atmosphere. And we could show for the aquifer of Basel and for different locations of this aquifer that as you would assume, it's dependent on the depth, where and the specific depth you don't see anymore the variability of the atmospheric influence. So we could quite nicely show for Basel that for most of the area it was not necessary to include the variance of these boundary conditions. Another highly instationary boundary conditions is the one is associated to the interaction with the river, and here we could quite nicely describe the measurements that we could quite good reproduce by conductance models that we applied to the river boundary condition. Concerning the aquifer, the anthropogenic boundary conditions, the most important questions that arose to us was what degree of detail we have to include in our models to capture or to describe the thermal influence of the boundary conditions. That is one of our main research topics we're currently working on. So if I come back to the motivation of our research, in many urban areas, not only Basel, there are many other cities like Karlsruhe, Berlin, Zaragoza, we can see elevated temperatures, and this can be proved that this is an effect of the surface heat island effect. But I think for the groundwater, the most important impacts are associated to the heating of subsurface building, and by the increasing use of groundwater for cooling purposes. To a less degree, it's the input via the surface or river groundwater interaction processes where also rising temperatures can be observed. Then we think that it's important if for the thermal use in urban areas, it's important to recognize the relevant processes that take place, to delineate the boundary conditions that are important, both natural and anthropogenic, and it is important to describe the thermal groundwater regime for those groundwater bodies and also the dynamics. That includes the seasonal variation, but when you come to temperature, it's also the retardation effects and memory effects that are important. And if you have those tools developed, it's possible to evaluate use potentials of the aquifer. And for the Basel, the city, it's also important for handling use conflicts, because you have the issue first come, first served. We see in Basel currently that many big companies, they try to put claims on the groundwater. They have big amounts of groundwater they want to extract, mainly for cooling purposes, even amounts of groundwater that's naturally not there, but they just make these claims for future needs. For the sustainable management of subsurface resources, we think that the concept of deriving a current state is important, but also to compare it to a potential natural state. Therefore, it's important to make field experiments and maybe also adapt monitoring systems. And at that point, I also want to highlight that for northwestern Switzerland, our working group has developed many models. It's not only the thermal heat transport models, but we have quite complex geological models. You can see here the interface of, we have the tabular Jura going to the folded Jura and the Upper Rhine Graben. And those tools actually allow to make quite quick, get an idea about the subsurface and also how heterogeneous the subsurface is. So we think also here it's important to capture and document the current status of these issues. What are our current activities? Currently, a colleague of mine is transferring the heat transport models to the entire area of the city. It's a corporate project with the Swiss Federal Office of Energy and the Agency of Environment. Then in scope of this cost actions, we had several STSM together with the working group of Pereira Enrique Vasquez and Alexandro Garza-Gil, where we tried to compare the cities of Basel and Zaragoza. And I actually hope to present some results of those studies, but the publication is still under review, so maybe next time. And in scope of this comparison of the two cities, we also tried to delineate those parameters that are important if we approach these kinds of problems. And we will also want to compare the two cities and to see which of the boundary conditions are transferable. So if you look at Zaragoza, it's also located at the Ebro compared to Basel at the Rhine. So the influence of the river is similar boundary conditions that we could consider. And compared to Basel, in Zaragoza you have cases where groundwater temperatures rise up to 27 degrees Celsius, but that are mostly punctual influences by thermal groundwater use. In Basel, you more have this diffuse thermal pollution by subsurface structures. That's the end of my story. Thank you for your time.
Thank you very much, Jannis. Questions, please.
Yeah, I have two questions. Very nice presentation, but I was very much surprised by the heating of groundwater by subsurface buildings.
Mm-hmm.
So my question, and I also was surprised by the thermal use of groundwater, because I think, being from Spain, I think of Basel as a cold city. So I would say, okay, thermal cooling during the summer is more than compensating by heating during the winter. So my question is, why is not? And second, in the heat transfer from underground buildings, how did you evaluate it to be so deep? How did you evaluate this source of heat into the groundwater?
Of the subsurface structures?
Yes.
Okay. For the first question, I think for many areas in Europe you see these elevated temperatures, and I think in cities also the buildings less and less need heating. So that's also why one reason is, no, I lost the first one, sorry. But the second one, I start with the second, you have to repeat the first one maybe. But the second one, how I implied the boundary conditions. We had several approaches. The one approach was with the heating degree days, that are days when the heating is put on. So when the temperature falls below 23 degrees Celsius, the heating is put on, right? So we knew the time when subsurface structures will be heated. And especially in Basel, you have many laboratories, so that are in rooms that have quite high temperatures. So that was how we implied this instationary boundary condition. And we had locations where we had the temperature measurement downstream of the subsurface constructions, and there we could calibrate general head boundary with the conductance value. And the first question was
how comes that cooling the water during the winter does not compensate the heating during the summer? Because
if you look at this pilot area, you have the river that's where cold water can come in, but only during flood events. So actually, for this area, you only have the diffuse input of the city area to the south, and this is a constant heat input.
So it's not about the heat pumps usual, but it's about the buildings which induce heat into the groundwater.
Right. Yeah.
Not by heat pumps.
Of course, in summer it can also be the other way around, that heat is extracted by the fluorines, right? If the gradient is the other way around.
So Linda, you want to say something?
Yeah, I also have a question about this legislative boundary that was set, 3 degrees up or down in the groundwater. Do you know on what information that boundary is based?
They throw dice.
Okay. Yeah,
No,
because this
it's not really on, and we have some new. I think it depends also on groundwater flow velocity. The heat input can be quite higher compared to the temperature change, depending on the groundwater velocity. So a fixed value of change down gradient is maybe not the right kind of tool.
Thank you, please.
I was wondering, did the city of Basel pick up your research and
yeah.
your results? Did they act on it, or?
Yeah, this work was financed by the Agency of Environment of the city of Basel. And
what effect did it have on city planning or city?
Okay. For the area I showed you with no more cooling, no more groundwater extraction for cooling purposes is allowed anymore. And also the rules for restricting the isolation of subsurface building is more strict now. So the C value increased. It's now 0.3 before it was 0.2. So that's what happened for the pilot area, and they're still waiting for the results for the whole city area.
Is the underground sewer system below the roads not influencing the groundwater temperature?
The underground
Sewer system.
they are more, of course, that's also a focus we're looking at. But then, of course, they're mostly located in the unsaturated zone.
Yeah, in Holland they are they are part always in the unsaturated zone. In Holland they are nearly always in the saturated zone.
No, but, we had contact with the people, and there are not many places where it goes down to the groundwater.
Yeah.
So groundwater at the northern part I showed to you is about 15 to 20 meters deep, and at the upper part it's deeper than 5 meters normally. So there are not many places where the sewer systems go deep. And what we also have, we have the district heating network, but also that they don't dig too deep. It's only 3 to 5 meters deep, and normally located in the unsaturated zone.
I think that there are, I have also several questions, but we are going to talk after. Thank you very much. So I'm